Thank you very much. It's good to be here with all of you, and I appreciate the opportunity to present our results from our LAUCC analysis. I wanted to give you a few quick facts about heat and health that maybe some of you did not know. Beyond a doubt, heat is the leading weather-related killer in the United States. It kills more than all other weather-related causes combined, including tornadoes, hurricanes, lightning, blizzards, and so on. On average, there are about 1,500 deaths per year from heat. Some years it could be 5,000 or 6,000, though. Other years it could be near zero. It's highly variable from year to year. Not surprisingly, urban area residents are particularly sensitive to heat, particularly because of the urban heat island, the type of housing, some of the problems that David just brought up, and so on. And also, this is most true in non-tropical areas, not in the tropics. This is one of those causes of death that is much more important in the Western world than in the Third World, and I'll explain why shortly as well. The urban heat island contributes to the sensitivity. That's one of the things we're trying to abate in the research that we are doing. And we noted, especially in a study, the LAUCC study, that there's a high variability among cities and neighborhoods. Some neighborhoods are much more vulnerable to heat than others from some of the issues, again, that David had brought up before. Now, the next point is maybe one of the most important. Summer climate variability is more important than actual temperature. That is, a place where it is hot all the time is not a place where you see as much heat-related mortality as a place where you have relatively pleasant summer temperatures, and then all of a sudden you get one of those weeks where it's 100 degrees. That's what kills the people, a highly variable summer climate. So I happen to live in Marco Island, Florida. The weather is the same every day. I'm looking at my little weather instrument now. It's 91.6 degrees here. Almost no one dies of the heat because that's almost our daily high temperature every day. But if you move to a city like New York, Chicago, and yes, Los Angeles, you have a much different situation. That's a place where you do get temperatures in the 70s and 80s most of the time in the summer, and then it goes up to 100. That's what kills the people. So more people die of heat in Los Angeles than in Singapore. More people die of heat in Toronto than in Phoenix, just to give you an example. Extended heat events and high nighttime temperatures are very important contributors. We sometimes think it's the daytime temperature that kills people. If there's no air conditioning and no relief at night and people have to endure a hot house during the sleep period as well, that can be very detrimental. Also, the number of days is important. If you have one bad day, or maybe even two, many people can survive it. But then when you get out to a longer and more extended heat event, that's what winds up killing people. And finally, which we are going to try to demonstrate today, we can improve the city's environment to lessen the negative health impacts of heat by several different ways that we will go through. Now, some of you may not understand the magnitude of this heat-related mortality problem. So what I've done here is I have strung together, let me get that arrow over here. This is every day's summer mortality of all causes, not just heat-related causes that David mentioned, but all causes in the city of Chicago, just the June through August period from 79 to 95. And as you look at it, you can see that approximately 3 people per 100,000 die of heat, with a little variation from day to day. You certainly could see every single heat wave, though. There are 3 right here. And you may say, well, that's just a little blip. How important is that? Well, if you go from 3 to 5 per 100,000, Chicago has 60 100,000s in the metropolitan area. It's 6 million. So multiply that 2 times the 60, that little blip is 120 deaths. And again, most of these are registered as heart attacks, strokes, and respiratory failure, not heat stroke or heat exhaustion. Medical examiners sometimes can't tell whether heat has killed someone or not. And then, of course, there was the big 1995 heat wave in Chicago, which was the granddaddy of them all. This is the one where they needed to bring in refrigerated trucks to get rid of the bodies. You can see we're up to 13 or 14 per 100,000. We'll be conservative. Let's say it's 13 per 100,000. Over the 3 per 100,000, that's 10 extra per 100,000. Multiply that 10 times 60, 100,000. That one line represents 600 extra deaths. So you can see you're talking about a pretty major event just in that one heat wave. As a matter of fact, that heat wave killed over 800 people in Chicago alone. And remember, I said the average in the U.S. per year is about 1,500. So if you look around the world, you can probably guess which the most vulnerable areas are in terms of heat-related mortality. And they're basically the mid-latitude areas. Notice near the equator, we don't have anything red around there. It's the west coast of the U.S., and remember, Los Angeles has a highly variable summer climate when you consider Santa Ana's. Even Seattle shows a signal. Then we have the northeastern U.S. out to about, let's say, Minneapolis, Oklahoma City, and so on. All of Western Europe is very vulnerable to heat because it happens so rarely. There's very little air conditioning. Then we have eastern China, where many of the major cities are. Same kind of climate as the eastern U.S. And we've done studies up to Siberia and have found this is a very sensitive area to heat. Then we have the New Delhi area as well. You can see India, and then the southern hemisphere, it's similar latitudes. They're also sensitive to heat. So let me tell you about the study now. The type of climatology we do is called synoptic climatology. It comes from the word synopsis. We look at weather situations. We don't look just like temperature and the humidity and the wind speed and the cloud cover. Every day is a typical air mass type. And you've probably heard of some of these. A Bermuda high sets in, and you have a moist tropical air mass. A desert air mass comes in, we call that a dry tropical air mass. If a cold front goes through, we call that a dry polar air mass. And what we have done, my team and I, is we've put every day over the last 70 years into an air mass type for hundreds of cities around the world, over 300 in the United States alone. Doing this, we find there are two air masses that are particularly oppressive. The first one is the dry tropical, DT, and the other is moist tropical plus. You'll hear us relate to these. The dry tropical represents the hottest and driest conditions found in any location. These desert air masses that occur to your east can move to the west when you get a Santa Ana in Los Angeles, or can move to the east on the other side of the Rocky Mountains. And the Rocky Mountains cause a problem to cities in the east because the dry tropical descends down the mountain range and then across the plains, and it gets hotter and hotter. So you can have 105 degrees in St. Louis with no problem at all. It's clear, it's dry, it's transparent, the solar load is incredibly strong. Then we have the moist tropical plus, which is what we are under in Florida all the time. This is an air mass that comes from the Caribbean and the Atlantic. It's hot and humid. The temperatures are not as hot in the day, but it stays warmer at night. We do have some cloud cover and thunderstorms, but the warm, humid conditions create sometimes conditions that are even worse than the dry tropical air mass in the eastern part of the United States in particular. So I want to make I need a little chart for you here so you could see particularly how these air masses affect everything. Let's start with New York City. 11% of the days in New York City are either dry tropical or moist tropical plus. On an average dry tropical day, there are an extra 16.6 deaths, extra almost 17 deaths. That's a 7% increase over the baseline. There are about 200 or 220 deaths a day in New York on average. So can you imagine on a typical dry tropical day, we have a 7% rise. On a typical moist tropical plus day, we have almost the same response. When you consider that 11% of the days are in these two air masses, in our research, we've discovered that there are hundreds of people who could die every summer in New York from the heat. Now, of course, these air masses sometimes occur rarely. In the summer, you have less deaths. More in other summers, you have more deaths. You go to Los Angeles, also a sensitive city, but not quite as sensitive as New York. 4% of the days are either dry tropical or moist tropical plus, and in that area, we have 5% increase on average, or 8.4 deaths on average in the Los Angeles County area, which is also significant. Now you go to Phoenix, only 1% of the days achieves a moist tropical plus or dry tropical level to cause any problems. And you can see that there's barely any moist tropical plus, so they have nothing here. And they do get a rise in mortality under dry tropical, but it only occurs 1% of the time. Rome, 11% of the days, it's a hot city, dry tropical or moist tropical plus. It could be cool or hot in the summer, high summer variability. Now you're looking at 14% or 12% increases in mortality because Rome is not as air conditioned, it has less green space, the people are less adapted to the heat, especially in terms of their urban structure. And that's also true of Toronto, where 7% of the days are in these two air masses. It's a smaller city, but 4.2 extra deaths represents an 11% increase in Toronto during a dry tropical day, and we have a 10% increase in moist tropical plus. These are no trivial numbers when you consider that we have all deaths increasing by this number in all of these major cities. So now the question is, can we cool our cities to lessen the number of deaths during these particular heat waves? And of course, we're going to answer that with a resounding yes. And one of the ways to do this is, of course, with tree canopy. And in this case, you can see this line represents kind of the temperature in the urban heat island and then the surrounding areas. Of course, it's hottest here, where you have evaporation, which was one of the cooling factors that David mentioned. In vegetated areas, the temperatures are cooler. Forested areas, the same thing. Even in suburban areas, evapotranspiration is very, very important. And shading and having evapotranspiration makes the city much more efficient if we can add these factors to the city, if we can add more reflection to the city where there's less absorption of solar radiation. That'll make the city cooler. So one of the things that's been developed, and it's a very important product, I work with 3M a lot on some of these issues, and 3M is one of the leaders in developing these products, is reflective roofing. There are materials you could put on the roofs within the shingles of houses, a granule that you can have included within the shingles of houses that can increase the reflectivity of the roof fourfold. The average roof has about a 7% reflectivity. If you can increase it fourfold to 28%, you can create an urban environment that's more pleasant. First, you need less air conditioning because less heat is entering the house. And air conditioning is a major urban heat island contributor. Think of those huge air conditioning compressors on the roofs of buildings that dump out tons of heat. And then if you just reflect the energy back into space, there's less being absorbed in the urban area, and that also cools the city. So this product is one of the many that are now being developed by 3M and other companies where we can actually increase the reflectivity or the albedo, which is a measure of the reflectivity of the city. They have reflective films on windows, reflective asphalt, reflective signs even, all kinds of products that can reflect solar radiation. So between the two things, the increased tree canopy and the increased reflectivity patterns that we can develop, we can truly make the city cooler. Now, it's not going to make a hot day comfortable, but if you can cool the city from 100 degrees to 96 degrees or 97 degrees, that may be enough in terms of the difference between life and death. And that's one of the major findings we have here. So in our study for LAUCC, we did a county-wide analysis that looked at the entire Los Angeles County and assumed similar prescriptions or reflectivities and tree canopies throughout. That was helpful to use the whole county because we had a very large sample of deaths. We did this for a large number of heat waves. We had a large sample of deaths we can work with. The bigger the area, it's better. The disadvantage is that we can't isolate how one neighborhood varies compared to another neighborhood because we use county-wide deaths for the entire county of Los Angeles, which, as you know, has millions of people. So then we went down to the district level. We used to call them neighborhoods, but they're bigger than neighborhoods. A group from Cal State Northridge of social scientists developed socially homogeneous areas in Los Angeles, and I'll show you the map shortly. And so we looked at each individual district, and in those districts we changed the roof albedos as well as the vegetation cover. The advantage was now we could determine the impact of socioeconomic factors on individual areas. The disadvantage is that us people, as statisticians, need large population sizes to do things. Sometimes the population sizes within such smaller areas are too small to really get meaningful or statistically significant results. So you want to do more of the district level stuff, but you've got to keep the district large enough to make sure that you have a big enough pool of deaths, heat-related deaths, that we could work with. So here are the 4 heat waves. We used different types of heat waves. Some were all MT plus days, hot and humid. Some were a mixture. One was less extreme. And then we had one very strong Santa Ana event dominated by DT days, because not all heat waves are created equal. One thing we're working with 3M on right now is to determine how their shingle materials react under different types of heat waves, because there is a high variation from one heat wave to the next. So we developed 4 mitigation scenarios, which we call prescriptions, using changes in tree canopy and solar reflectance, assuming different levels of roof reflectance and street reflectance. And in some cases, we had low tree canopy, high solar reflectance, high tree canopy, low solar reflectance, and so on. And then we had our pie in the sky, where both were increased considerably. So RX4 is the best scenario, where both the albedo was increased because of use of these roof products and the tree canopy was increased. And then I worked with a modeler at Arizona State, a gentleman named Dr. David Saylor, who models climate if you input certain assumptions involving the albedo and tree canopy. He can tell you what that is going to do to the meteorology of the urban area. So here is one of the outputs. We did this for all the heat waves and for every one of the 4 prescriptions. This one happens to be the low tree cover, high reflectance one. And here we're looking at the air temperature 2 meters above the surface. The heat wave, this one was the August 26, 09 heat wave for 11 a.m., 1 p.m., and 5 p.m. As you can imagine, the darker the blue color, the greater the cooling that you have. So you could see what's happened at 11 a.m. We're getting already up to a degree or more cooling, degree centigrade or more cooling throughout the Los Angeles basin. And by 1 p.m., you could see it's considerably higher, mainly inland. These arrows are the wind field. And of course, the wind is blowing the cooling effect inland, as you can see. And this is what we want to see. The strongest impact is at 1 p.m., where you're getting more than 1 degree centigrade, or about 2 to 2.5 degrees Fahrenheit in terms of cooling in most of the populated areas. And then by 5 p.m., when the sun is getting lower in the sky, we have even more dispersion because of the wind, and you can see that the effect is becoming decayed a little bit. But nevertheless, we did this for every single scenario of every single heat wave, and we have maps like this for all of them. So here are the results that we have. And this was the Santa Ana event for the countywide area, which was September 2010. You can see RX0, which is the baseline, assuming we did nothing. And then you have RX1, 2, 3, and 4. We mentioned what those were. So this is what really happened. This was the DT event. There was an MT day at the end of it. You could see what the temperatures were, and you can also see what the mortality increases were above the baseline. Now, in some cases, in some of our events, we actually had an air mass change. The temperature was cooled maybe even a degree or more, but it took this DT air mass on the first day and moved it to a much more benign, dry, moderate air mass, which does not historically kill people. And what that did to the mortality is the baseline was 5% increase. It went down in the 4s, and then to 0. We actually cooled it enough in our estimation, remember these are model data, to actually remove the heat-related mortality. And you can see on every day, especially with prescription 4, the percent mortality increase was down in all of these places. So for all the heat wave, we went from a 12.4% increase in mortality. By the way, an average in Los Angeles, there are 150 deaths per day, so there's a total of 600 deaths here, 4 days. 12.4% of 600 deaths means that this heat wave, in our estimation, caused 74 extra deaths. And under prescription 4, we reduced that to 8.8%. 8.8% of 600 is 52 extra deaths. So if we could change the city to mimic prescription 4, we could save 22 estimated deaths from this heat event. That's really quite an accomplishment, and it's a 29% decrease from the 74 that we had before. If we can do this in one heat wave, What do you do with every heat wave? The point is that we got some results that were as good as this, others were not quite as good, but you can see that we can make a major reduction based on our modeling of heat-related mortality. So then we went to the district level, and these were the two social scientists who helped us out considerably, Dr. Kim Kerner and Reagan Moss. They were the experts. I am not an Angelino, so obviously we needed them to make the areas socially homogeneous for us. And we divided Los Angeles County into smaller socioeconomic homogeneous districts. Based on what I know about all of this, we need a population of at least 300,000 for each district to minimize the non-meteorological variation, such as a major car accident or something like that, which can throw off our data considerably. And so there was a challenge that Dr. Kerner and Moss had to go through to make our areas homogeneous socially and to keep it at 300,000. And here are the districts. We initially divided LA into 18 homogeneous districts. Dave Eisenman gave us the data. They had to be by zip code because the neighborhood mortality data are at zip code level. And so these are all the districts. Some were relatively wealthy with low density, like number 18. You can see that's a mixed white-dominated neighborhood with low density and low poverty. Some were high poverty, high density areas with minority populations. As you can see, 5, 6, 10, 11, and 1 are those particular districts, and you can see those all have high density, high populations. So virtually we were able to evaluate the high poverty districts and compare them to the low density, low poverty districts to see how the results would differ. Let me give you an example of some of our results. Now you may remember, let me go back and show you District 11 is one of our poorer districts, Hispanic minority. And these are the actual results we got when we changed these prescriptions for the district only. And I'd like to add, we didn't do it for the rest of LA, we just did it for the district. We probably should have done something to the rest of LA because we made the assumption that the rest of LA was perfectly the same as it is now and just changed the albedo and canopy cover just for the district. So I would expect a more realistic thing would be to change at least something in the rest of the city. Therefore, I would consider these numbers very, very conservative. We had temperature reductions, but most importantly, we had mortality reductions in this 2006 heat wave. You could see that we estimated that in that district, based on our algorithms, between 4 and 5 people died during this heat event. And sure enough, these numbers are reduced significantly until you get to RX4, the most aggressive, high albedo, high vegetation prescription. We're down to 2.73. That's a reduction of 40% under 4.52. So it's important to note, again, this is one single heat wave. Imagine if we get results like this over a whole slew of heat waves, both county-wide and district-wide. Edith and her group at Tree People are much more innovative from an artistic standpoint than I can ever be, and they developed these visuals to show us the decreases that we had between the baseline and the prescription number 4. And you could see that most of the results are in line to what we might expect. Some were surprises, and we don't understand a few of the surprises. I'll bring them up to you. But 18 is a district that's wealthy, low population density. We had almost nothing, no result. And then you could see District 5, which is one of our poorest, had a very strong result. District 11 had a moderately strong result. District 16, which is not necessarily a poor district, but a very hot district, to the north of Los Angeles, also had a fairly strong result. The big surprise for us is District 10, which is a poverty-oriented district. We had no really diminishment of mortality there in many of the heat waves, and I'll tell you right now, we don't understand it. We've talked to some people in LA about this. We want to research it further. David checked the data to make sure that there wasn't a mistake in the data. There was not. So we are not sure why District 10 came out the way it did. This is clearly something we have to explore. But for the heat waves, you could see that the poorer districts, 1, 5, 11, and then the hot 16, came out strongly, 10 did not. And again, these are results that are generally what we expected. They were generally intuitive, but there were some non-intuitive results which I and my colleagues can't explain. So then the final thing we did, as Edith had mentioned, is that if we can cool the city by a couple of degrees, how much can we delay climate change if we can do this with present technology? Everyone would agree, whether you're a climate skeptic or not, that if we can cool the city today and save lives, that would be a very important thing. So what we did is we used two models that are used by what's called the IPCC, the Intergovernmental Panel on Climate Change, which is a UN agency that deals with climate change. And we used two models. One was called a business as usual model. That means everything stays the same as it does today, and we don't improve our gas emissions and so on, and so climate change proceeds apace. And then we used a moderate mitigation model where we do cut back on CO2 emissions, for example, and do control for it a bit. So this was easy to do for us because we know that RX1 on average in LA County reduced temperatures by 1.1 degrees C, RX4 by 1.7 degrees C. We needed to find how many years down the road would the models increase the temperature, the climate change models increase the temperature by 1.1 or 1.7 degrees. So we'll go straight to RX4, which is our more aggressive. Using the business as usual model, it estimates that in 43 years, the temperature will be 1.7 degrees higher in Los Angeles than it is today. Well, if that's the case, and if we can cool LA by 1.7 degrees using the fourth prescription, we can delay climate change by 43 years. Think about that for a second. Can you imagine if we can give science 43 more years to come up with a way to deal with climate change? That's enormous. By the way, if we do abate our gas emissions and have the moderate mitigation model, that changes it to 107 more years, because it will take 107 years, if we use this prescription 4, to reach 1.7 degrees centigrade warming. 10 decades. So as you can see, all the prescriptions mitigate this by 2 to 3 decades using business as usual, and 6 to 10 decades using at least a partial mitigation. That is really an important fact to know, because I don't care who you are and what your stand is on climate change, if in fact we can do this kind of thing, we certainly have done something very important. So let's summarize the results. In general, lower income, more densely populated districts generally demonstrated the greatest increases in heat-related mortality when we did our evaluation, districts 1, 5, and 11 in particular, not 10. These districts also showed the greatest benefits from the use of cool solutions based on the darkness of those maps that Edith and her group created. There were some unexplained exceptions, particularly District 10, which showed little impact, and then the wealthier but very hot District 16 showed a greater impact, but maybe it's because that's a particularly hot district and it's not always hot. There's still high climate variability there. Use of cool solutions can delay climate change by at least several decades in Los Angeles if we use the latest models that the IPCC uses. And my concluding remarks are, the importance of heat on human health cannot be overstated. Heat is a silent killer. You don't see devastation in urban areas like you do with a hurricane or a tornado, so you don't even know that heat has killed that many people, yet the deaths mount. So it's often understated. We must gain understanding about the regionality of the problem. We need to know how the urban heat island reacts in terms of heat-related mortality, and also the potential impact of climate change. We've been doing that for quite a while with climate change. And very importantly, for those who are skeptical of climate change disaster, we always emphasize that heat is already the largest weather-related killer, and right now we have the technology to lessen the impact of heat-related mortality using the things that I just showed you. I'm very happy to tell you that I have gotten phone calls from several different urban areas that want to do this kind of evaluation. Edith, David, and I participated in a workshop in the Twin Cities last fall. They're one group that's very eager to do this. Probably my most enthusiastic group are in Madison, Milwaukee, Wisconsin. We have been talking monthly. I actually have a University of Wisconsin graduate student working with me to start and determine how these benefits might affect this area in Wisconsin. You might say, isn't that a cool area? That is just the kind of area that is vulnerable to heat-related mortality. There's less air conditioning and so on. And I just got, a couple of weeks ago, a call from Miami-Dade and Broward counties, and they have asked if we can move forward on this kind of procedure as well. So I'm talking to them right now as well, and we're looking for possible funders for this particular study. So I'm glad to say that 3 major cities would like to move forward with this. And then finally, and very important, LAUCC was so unique and so wonderful to me as an academic, a longtime academic, because there were guys like me, the private sector like 3M, government entities, city and state government people, and nonprofits like Tree People and Climate Resolve all worked together. They all united to tackle this problem and come up with adaptation and mitigation policy options. I was really very proud of the coordination that we had among all of us. And then finally, if you go to the Tree People site, our final report, which has been submitted to the Forest Service, who kindly funded the project, and Harvard-Westlake School, is right there, along with a beautiful infographic on the work we have done. You will see in greater detail all of the study that we did in either of these products. And again, I thank you for your attention. That was very enjoyable for me and for all of us.